Go live. All right. So are you ready to go, John?
Yeah.
Okay. So thanks everybody for coming to the Augusta University Colloquium series we've been having for the last 2 semesters, and I think it's been going pretty well. And this is sort of, I think, the 9th one this semester, and we've had some pretty good talks, and we still got a few more left. Not to mention, I'm really excited, especially that John Sterling's here to give us a talk on his work on logical relations as types. And currently he's at Carnegie Mellon University working on his PhD with Bob Harper. And so I think this is going to be really cool talk. And I've been pretty excited about hearing about this work. So I'm just going to let John go so he can have the maximum amount of time. So thank you.
Thanks, Harley. Yeah, I'm really pleased to be able to speak to this seminar about the work that Bob and I have been doing over the past year. Let's get started. So from time to time, I like to think a bit about why it is that we're doing the research that we're doing. Not just like get the paper, get the job, although I do hope I get those things, but more so like what people are we helping and what methods are we using to help them. Coming out of a several-year experience as an industrial software engineer before entering the academy, what I came out with that was that software engineering is about division of labor. It's about the division of labor between users and machines. Which things can the user count on the machine to handle appropriately for them, and what is the degrees of freedom that the user has when interacting with the machine. There's a division of labor between clients and servers. And then there's a division of labor between different programmers or different teams that are working on the software. And my perspective is that many of these can be at least partly addressed by considering the division of labor between different modules. And the reason that software engineering and programming is not a solved problem is that we have this contradiction between abstraction, which is how we execute a division of labor, and composition, which is how we put the labor together. Abstraction is about forgetting things that you know in order to avoid depending on them. But sometimes when you forget too many things, then you might not be able to plug things back together again. And composition is about having components that can work together to achieve a goal. And I think that PL theory in particular is basically a particular hypothesis that it is possible to substantially resolve or partly resolve to a great degree these problems by means of linguistic solutions. And I think that this idea was stated very eloquently in different terms by the great John Reynolds in his famous paper of 1983. And I think that, my experience, and I guess Bob taught me this, modules are a really good way to investigate these questions because they concentrate many of the most problematic aspects of these things into a single place where you can study them. And so what I mean by modules are, well, I'm trying to be pretty big tent right now, but the kind of stuff that appears in standard ML, OCaml, even Racket has some form of modules as well. Technical differences, of course, but this is the perspective that I want to work from. So let's start to be a bit concrete. So we can consider a basic functional queue data structure, an abstract data type where there's a type component that's the representation of the queue. There's operation to construct the empty queue. You can enqueue something. Here I'm just considering queues of strings, but obviously you could do something else. And then there's an operation to dequeue. So if the queue is empty, it'll return none, but if it's not empty, it'll return some together with the oldest element and the rest of the queue. And a particularly naive way to get started with implementing the queue is just as lists. So you have insertion is really easy. You can enqueue things by just putting them on the front of the list. But the problem is that with the linked list data structure, it's really easy to get to the front and really hard to get to the back. And so when you want to dequeue something, it's going to be pretty bad. You've got to reverse it and then pull it out and maybe reverse it again. And maybe there's a slightly better way to do this, but this is basically what happens if you try to do a ListQueue. But it's a good functional, like it's a good reference implementation, even if it's not performing well. And you can also consider a better, slightly better data structure, which is where you have two lists, and one of them represents the front and the other represents the back. And so you can add to one of them, I guess the one on the right, you can add to that one, but then you can pull from the other one. And the idea is that one of them is reversed in relation to the other. This implementation of the queue data structure has a better amortized complexity because you don't do as many reversals. You basically only reverse when you run out of elements, and then you flip it, and then you go. So this is pretty good. These are actually not the same, of course. I mean, you can see, like, you can look at the type components, and the type components here are different. So these are not equal, but we have an intuition, and in fact, like a fact for many programming languages, that any code that you write that is implemented without knowing which one of these you're using, it will behave the same no matter which one you're using. And understanding that possibility, that there could be two things that are different and yet not different in an observable way, is, I think, the essence of what we do in programming languages. And so one possible way to define this, there's a variety of other ways to define it too that are all okay. But two implementations of a data structure, I would call them observably different if I can make a function out of all implementations of the data structure and have that function do a different thing on, or make a different observation on one versus the other. And I use the type of booleans here as my type of observations because they're discrete. There's just true and there's just false. And so you can have the computer print out which one it returns, so you can actually see what the observation was if you want. In a language with non-termination, you can also just have it be a function into unit, and then you could talk about do these co-terminate and so on. And when there is no term that would when there is no program that could distinguish between them, then we call them observationally equivalent. So the theorem that we would want to prove, which would justify being allowed to just swap in a better implementation of the queue data structure, is that for any program that computes a Boolean from an implementation of the queue structure, it computes the same Boolean on both ones. And the goal of this talk is basically to understand how to prove this. Well, with slightly more ambitious goals than that, but that's where we'll start. So this idea that things can behave uniformly in their type arguments, even when the type arguments are different, it's really hard to actually formalize what that means, because naively you start saying things that are not really like well typed. But the idea was always present, and even like in the late 60s, when Chris Strachey, one of the founding fathers of programming languages, wrote his excellent, I guess, lecture notes or monograph on programming languages. He used this word parametric polymorphism to describe polymorphic functions that are uniform in their inputs, whatever that means. And I think one thing that probably not many people are aware of, it surprised me, I was thumbing through the notes from a very old obscure workshop, is that Lembeck was also trying to understand the same thing. And I don't think that Lembeck knew of this terminology because he didn't cite or mention it, but it was around the same time. Lembeck was trying to understand the sense in which derivations in, say, propositional logic are somehow generic in the atomic propositions that they refer to, like P and Q and R. And I think it wasn't until the early 80s that John Reynolds famously introduced this relational parametricity concept to formalize the intuitions that had been grasped by Strachey and Lambeck and so on, with something that was actual mathematics that you could actually like test things about and improve things and so on. And this was maybe the beginning of a new era for programming languages. So basic idea was that you have your programming language, maybe a polymorphic lambda calculus or something like system F or whatever, and you're going to give an interpretation where you interpret a type as basically a logical relation. And what that means in this context, I'm trying to be very like not use a lot of words that aren't clear, is that you have the collection of closed terms of any given type. And one of these relations, which I'll call a parametricity relation, is going to be just an arbitrary relation between the closed terms of two different closed types. And I'll call one of them the left type and the other the right type. And these types are coming from the syntax. And now the idea is that we have a model in which the types are given by these relations. So the first thing that we have to do once we define a concept is we have to say what a function between two instances of that concept is. And so a function between two of these parametricity relations is given by closed terms that are functions from the syntax, both on the left and on the right, okay? And then the additional fact that these functions together preserve the chosen relations. So if you have two elements, left and right, that are identified by our sigma, the first parametricity relation, then when you pointwise apply the functions to them on the left and on the right, they're related by our tau. And this preservation of relations is basically how, it's what makes it all work. And you can interpret the connectives of, say, lambda calculus of polymorphic type theory in this way. There's a function relation that basically internalizes the notion of a function between two relations. And with this definition, it's very easy to see that it satisfies the laws of an actual function type. So that's good. The Booleans, well, if you have the Booleans in your language, which I think it's convenient to have them in order to have a poll for observations. This is, there's a lot of options, but I think a good option for interpreting them relationally is that they're both, so you put the Booleans on the left and on the right, and you say that two Booleans are related when they're both either true or they're both false. Again, you could choose other options, but this is a good one. And then maybe the most important one for Reynolds' setting was to interpret universal quantification over types. So given a family of relations that I can make precise in some way that I'm not going to bother with right now, you can take essentially the intersection of that family of relations. And what it does is it says that two polymorphic functions on the left and the right are related when they preserve all relations. And so that's a very powerful fact. And this is basically the place where parametricity happens. And just as a little example, you can very easily, with this model, you can then prove that if you have a polymorphic function that computes a Boolean from an element of an arbitrary type, okay, where you quantified over the type alpha, then this function has to do the same thing if you pass it, say, the unit type, or if you pass it the Boolean type, and likewise with really any other type. And the way that you always solve problems like this is first you unfold what this means in the parametricity model. So you have all this junk about relations. And then usually it's starting off with quantifying over all relations. And then you pick a really smart relation that solves your problem. And so we'll pick the relation that just contains, that only relates the element of the unit type with true. And if we pick that relation and do some more turning of the crank, the conclusion here ends up literally being this. And so you're done. And so the thing that we wanted to prove is more hard than this, but it's basically the same idea. We wanted to prove that ListQueue and BatchedQueue behave the same with respect to any observations. And if we want to do this in the Reynolds setting, well, first we've got to translate this into a language that Reynolds parametricity makes sense for. So get rid of this, like cool Q module thing. And since we have it on the left of the function type, we can just be quantifying universally over the representation type and the operations. So here's the Q representation type. Here's the empty Q. Here's the NQ map. And here's the DQ map. And then here's the result. And then we're going to instantiate the interpretation of this in the relational model. So we're going to instantiate this part here with a representation invariant, which basically says it's going to relate a ListQueue to a BatchedQueue when the BatchedQueue, if you fold it back up into a single list, is the ListQueue. And that's the invariant. And then you have to instantiate the other arguments. You got to put in one for here and one for here and one for here. And the interpretation, the relational interpretation of the function type means that in order to instantiate one of these functions, you basically need to, you'll provide, the ListQueue empty and the BatchedQueue empty, but then you'll also have to additionally provide the fact that these are related in the relation. And likewise for the insertion map, you have to show that the insertion map is going to respect that invariant. And once you do that, then you can get this result. And like all of these things, these are statements about things being related in just some arbitrary relation R. But the reason we're able to get an actual equality at the end is that we define the Booleans along the diagonal. We define them in such a way that Booleans are related to each other when they're equal, not like for some other weird reason. And so that's how you do this. So this basically works, but I feel that like it's a bit artificial because when we are working with modules, we don't think of like quantifying over all the representation types and so on. A module for me is just like it's basically an element of the type, and it happens to have a way to project out from that element a representation type. Modules used in practice are closer to dependent types than to polymorphic types. So for instance,
one question we have on YouTube was what notion of equality are you using in those expressions that you're showing?
Good question. I'm trying to be a little bit agnostic right now, but personally, I like to just have an equational theory that includes the beta and the eta laws for the connectives if they hold. But of course, as you add computational effects and so on, you may or may not want to have a different notion of equality, one that, for instance, is based on transitions and so on. And one way to deal with this is basically to factor out the effects into a monad using like Moji monadic meta language or LATS modality. And then the interpretation of the logical relation for the monad itself would relate things up to whatever transitions are necessary. And that's one way to deal with the problem. But yeah, that's a good question.
Great, thank you.
Sure. Right. So continuing here, it is possible to interpret these modules as like existential types. And there's the famous slogan that abstract types have existential types. And that's fine. It works. But it is a bit brutal because, well, for one, it doesn't directly justify the notation of where I have a module and I just project out the type, the representation type, for instance. And that falls out when you do a very complex program transformation involving like continuations and stuff like that. So for me, I would prefer to be able to reason about the code as written. So I would like something that actually interprets the notation q.t. And so for that, I don't use existential type because that is basically the only way to eliminate an existential type is to just unpack it into the scope. But once I've done that, I can't put it back together again. So if we wanted to do this, basically, we would need a logical relation over the collection of all types. And what we would need it to do is somehow, if two types are related in there, we would somehow need to know what relation they have. And this is a very strange thing to say about relations. Of course, it doesn't really make any sense because you can't have a relation of relations. It's not a size issue, it's a dimension issue. Two things being related is at most true. So you can't store information inside the fact that two things are related. So that's not really going to work out. But an idea that has been becoming more and more popular over the past decade or so is the idea of replacing relations altogether with something where you can store data in the fact that two things are related. So I think this is a very good idea, which really helps with developing the theory of modules. So roughly the idea, at least as we are looking at it, there's a variety of ways to do this, is that rather than having a relation between the closed terms of the two different types, you just have a family of sets and it's indexed in the closed terms of two different types. And taking the fiber of that family of sets over two particular elements of the left and the right type, you get the collection of proofs that those two things are related. And there can be more than one element in that set. And that's how we're going to store the additional data we need in order to account for the parametricity structure of types. And so here, I'm going to stop saying parametricity relation and talk about parametricity structures. And really, these work exactly the same way as they used to, in the sense that you can interpret the parametricity structure of a function type by replacing the universal quantifier with the pi and the implication sign with the function arrow in set theory, and you're done. And likewise for the Booleans, we just replace the disjunction with the coproduct and we're good to go. But what's new here, what's new is that now we can define the computability structure of the collection of all types with some asterisks here. If we have a universe of small sets in our ambient set theory, we can then use that to define a family of sets indexed in pairs of closed types, and over a particular pair of closed types, sigma left, sigma right, the data that we store is going to be small families that are indexed in the elements of sigma left and sigma right. Now, this approach doesn't, as I'm presenting it, it doesn't model impredicative polymorphism, although you can relativize this construction from set theory to a different topos, and then it will model impredicative polymorphism if you want. But for me, I'm not worrying about that because personally, I don't find the impredicativity to be that important for my own applications. But yeah, let me not worry about that. So this is nice because now we can interpret the queue structure directly into this, not as like some CPS universal quantification, but instead as a dependent sum in the sense of type theory. So it's literally like, well, you've got a type, and then you've got some things involving that type. And there is a projection operator that projects a type from any queue implementation. And so that's very nice and compositional. So basically, all of this works, and it simplifies the parametricity arguments for things like the queue structures, in the sense that you can do it directly on your code, and so that's very nice. But it's also very painful because anytime you want to prove a theorem, you have to interpret it into a fairly complex model, and we've actually just been making that model more and more complex as we added all this proof relevance and stuff, and so it starts to get out of control, in my opinion. And I think the thing to do at that point is to start investigating the structure of the category of parametricity structures. That is, like, we know what a parametricity structure is, and we know what a function between parametricity structures is. And so let's figure out what properties those things have. And then perhaps we can abstract them in order to get a language that is easier to use. And that's basically what Bob and I ended up doing. We call the result a language for synthetic parametricity arguments, because it's synthetic in the sense that like classical geometry, from ancient Greek geometry, was like you assume axiomatically that there's like a thing called a line and so on, and then you come up with axioms that accurately describe the way that lines work, and then you use this to prove things. And analytic geometry, which was developed much later, is the idea that, well, you actually just have point sets, and you can arrange those point sets in various positions so that they form lines and so on. I see that as analogous to here because in the traditional like Reynolds style parametricity, what we have are sets or assemblies or things like that, and then we can arrange for those things to have parametric structure by turning them into relations and doing families and things like that. But it's not a direct treatment of parametricity. So what we want to do is find like what are the lines and circles and squares of parametricity, and that's basically what we're doing. So I like to think of what Reynolds was doing as saying types as logical relations, in the sense that like what is a type? Well, we interpret it to be a relation, and that works very well. And Bob and I, well, we decided to try and flip it around the other way, where instead of figuring out how to interpret types, we instead figure out how to interpret logical relations. So here we actually just assume that everything in sight is a logical relation. And then what we're going to do is try and understand which ones of those are corresponding to pieces of syntax and which ones of those are corresponding to things from semantics. And what we were very surprised to learn about as we studied some ancient literature is that there is a very nice modal theory that allows you to do this. So starting from an existing concrete or analytic understanding of parametricity structures, what I want to do is start isolating some structure that then we will take as a definition. So if I have a parametricity structure, and if you're not comfortable with structures, just think about them as relations. It's okay. If I have one of those, suppose that that every two elements of the left and the right types are related to each other in exactly one way. So there's no two things that are not related, and and there's no two ways for there's no two different ways for two things to be related. In that case, we call the parametricity structure purely syntactic. And basically, it just means that, like, well, the semantic data of all the fibers is just units, so it doesn't really do anything. And the interesting stuff is happening at the level of the left and the right syntactic parts. Now, on the other hand, we can also talk about something that is degenerate in the syntactic direction, as opposed to being degenerate in the semantic direction. So purely semantic parametricity structure would be one where the base, the left and right syntactic types, are both the unit type, or something that is isomorphic to the unit type. And there's this remarkable property that every parametricity structure, well, maybe it's not so remarkable if you literally constructed them in the way that we did before, but it is quite profound, actually. Every parametricity structure can be turned into one that is purely syntactic or degenerate in the semantic direction, and one that is purely semantic or degenerate in the syntactic direction. And on the other hand, if you have those two parts, you can actually glue them back together and get your original parametricity structure. This is basically, well, this is what is often called a fracture theorem in mathematics, and it comes from the Grothendieck school in algebraic geometry in the 1960s. This is basically what we're going to take as a definition of parametricity. And this operation that wipes out the syntactic part or wipes out the semantic part of a parametricity structure, these can be seen to be modalities in a type theoretic sense. And they're really nice modalities. They're called Lex idempotent modalities, which means that they're monadic. They, if you do the modality twice, it's the same as doing it once. And the Lexness means that they preserve equality, which is wonderful. And yeah, so it's a like best kind of modality you could ever hope for. And so that's very nice. And there's a further remarkable property that we'll use to actually restate those modalities, which is that there is a very strange parametricity structure, which Bob and I have called the syntactic lock. And it has this weird property that exponentiating by it is the same as projecting the syntactic part of a parametricity structure. And so if you put that in the context, all of a sudden, all the semantic stuff that you were doing is gone, and you're just only looking at syntactic stuff. And roughly the way that this works is that the syntactic parts, the tau left and tau right of this thing, are both the unit type. And the semantic part is the empty type. And if you can kind of imagine what happens if you put one of those guys into the context, well, as far as the syntactic stuff is concerned, putting unit on the left of the turnstile doesn't do anything. So that's OK. It doesn't change the syntax. But putting 0 or bottom on the left-hand side of the turnstile, that just wipes everything out, because under the assumption of bottom, then everything is equal. Everything is isomorphic to the unit type. So this is the sense in which it kills the semantic part of a parametricity structure. And we can use this as a definition. So we'll define syn to be this function type. And we can define sem to be a more complex thing. And it's called a join, which is basically you take the coproduct and then you quotient by the intersection. But it's not so important today to understand that construction. And maybe even the bigger takeaway here is all we need to talk about parametricity is just plain old ordinary type theory, but with this one little thing added. And that gives us, that just automatically unleashes all the structure of parametricity without need for any complicated by hand constructions.
So one question, John, sorry, from YouTube again. Does purely syntactic sort of mean you don't get anything extra by generalizing from a relation to a family of sets?
That is one of the consequences, yes, because like a purely syntactic thing has unit as a semantic part, and unit is also proof irrelevant. So these aspects do coincide for that.
Cool, thank you.
Sure. So what Bob and I did is we actually just did this literally. We took ordinary extensional type theory, and you could do it with intentional type theory. I have some secret hacking in Agda, which is fine, but just to keep it simple, we use extensional. And then what we do is we add to it one of these magical propositions. And well, I kind of lied when I said you only need this syntactic lock, because we're doing binary parametricity. We want to have a left side of things and a right side of things. So we'll actually add a left syntactic lock and a right syntactic lock. And what the left syntactic lock does is intuitively it wipes out everything that's not left syntactic. Everything else just disappears. Okay. So first of all, left is not the same as right. The disjoint places, and so we formalize that by having the axiom that if both of them are true, then everything is true. Okay, and then we say that the syntactic lock is just the disjunction of these two disjoint propositions. And the idea being that then to construct something that is syntactic, it suffices to construct on the one hand something that is left syntactic, and on the right hand something that is, well, right syntactic. And then we define the modalities for syntactic things and semantic things as before. And this has the property that the syntactic part of a semantic thing is a unit type, that was how we defined that notion before, but now this is a consequence of the definitions. And yeah, you can define syntactic things by case analysis on what side you are currently on. It's kind of a subjective thing. It's like, am I on the left or am I on the right? And this is the notation that I'm going to use for that case analysis. And we use this to prove parametricity theorems. In fact, there's one more part that we use, which is helpful. We can define a connective that, so given a parametricity structure, which is now just literally a type in this extended language, and an element of its syntactic part, I'm going to define something that I call the syntactic extent. And this is basically going to be the type of all elements of A that have the same syntactic part as little a here. You can define this as a subset type or a singleton, a subset type or a sigma type, as you please. And by the way, this has the property that underneath the syntactic modality, this becomes a singleton type, a type that has exactly one element, because underneath the syntactic modality, this becomes true. And so then it's saying it's the collection of things that are equal to A. But of course, there's only one thing that's equal to A. It's A. So this becomes a singleton underneath that modality. So like, how do we actually use this thing? Well, if you have an actual language that you want to prove a parametricity theorem about, what you do is you axiomatize that language in the language of paramtt as a dependent record. And it's going to be the dependent record of like implementations of all the constants that exist in that language. And so for something like lambda calculus, typed lambda calculus, what we do is, well, the syntax of typed lambda calculus has a collection of types. Okay, and then for any type, there's a collection of elements of that type. And then this is closed under function types, which I call R for arrow. Okay, and then has lambda abstraction here. And we're using a higher order abstract syntax, which is actually justified here. You have lambda abstraction. So if you have an element if you have a function from elements from sigma to elements of tau, then you have an element of sigma arrow tau. And I actually bundle in lambda abstraction, application, beta reduction, and eta expansion into one object here, which is what this isomorphism states. But you can cook it up any way you want. It's all good. Maybe we'll add a Boolean type and just 2 constants. We could also add an if statement, but I'm not going to bother with that today. It's enough just to have some constants here. All right, so this is basically like an LF presentation for people who are familiar with logical frameworks, but with the additional ability to specify equations between things, which correspond to the ways that things compute. And so once we have the language defined as like a data type or a record in paramtt, to prove a parametricity theorem for it is to implement a function that takes a purely syntactic implementation of your language, so something in syn of L, and turns that into a total, like a parametricity implementation, something that is not just syntactic, but whose syntactic part is exactly the thing you started with. And so we use a syntactic extent here. What is the intuition of this thing? Like, why are we doing this? So think about how some of you may have proved parametricity theorems or logical relation arguments in the past. And what you do is you define an interpretation, usually by recursion on the type structure. And so, for instance, you have to say, what is the logical relation at the Boolean type? And what is it at the function type? And so on. And one of the things that you do is you don't just assign a random relation at the Boolean type. It has to be a relation between elements of the Boolean type, okay? And you don't just assign a random relation to the function type. It has to be a relation between elements of the function type and so on. And likewise, when you're proving the soundness theorem, when you want to show that true is related to true in the Booleans, you are showing that true is related to true, not that some other things are related to true. And so the use of the syntactic extent here is capturing that aspect of the conventional logical relation argument. Because you start with the syntax and then you construct the parametricity structure over that piece of syntax, not some other piece. This is basically what we do. And so if we were to abstract over this M and then try and build this thing, which we're about to do, that'll give us some intuition for what it looks like to construct these things in paramtt. So before, we showed the parametricity structure of types as in the analytic setting. And we can give an analogous structure in the synthetic setting. And it's almost going to look tautologous, which is nice when that happens. So what we're trying to do is we're trying to say what this M star, I'm going to write M star for the parametricity model corresponding to the syntactic model M that we started with. And we have to define what a type is in M star. So based on our definition of that L thing, it needs to be an actual type in the paramtt universe. And because we're trying to make this M star thing be aligned over M in the sense of having its syntactic part be literally M, when we're defining this component of M star, we need it to be having its syntactic part be the corresponding component of M. And so we need to define a parametricity structure whose syntactic part is literally M.type, where M.type is a syntactic thing. So I'm just going to define this as another signature or dependent record in the language of paramtt. And here's what I'm going to do. I need to have a syntactic type, okay, in here, because a parametricity type has a syntactic type. And remember, we're using the syn modality here, so this is actually a pair. It's going to have a left part and a right part. But the beauty of this approach with these propositions is that all of this left and right stuff can be just tucked away. And in fact, we could add a third position. We could have ternary relations, and it actually wouldn't change our constructions at all. So that's really nice. So we'll have a syntactic part, which is a syntactic type. And then we're going to have the parametricity part of this. And that's going to be a parametricity type, U. And I'm just assuming that my system can resolve universe levels that make this make sense. So this is maybe big U and this is little u, but let's not worry about that, okay? So we have a type that is going to be the parametricity data for the syntactic part, and we need to make it aligned over the original syntactic part here. And basically, this is saying that this type determines for every element of the syntactic type that we started with, it determines some data for that, which says when it is parametric. And we use the syntactic extent to ensure that it's about syn and not about something else. And now, how do we know that this whole thing restricts to m.type? Well, what we need to do is consider what the body of this thing becomes underneath the syntactic modality. Well, because the syntactic modality is idempotent, this first component doesn't change. Now, what happens when we put the second component under the modality? The second component becomes a singleton, because there is, under the syntactic modality, there is exactly one thing whose syntactic part is m.l of syn, and it's m.l of syn. That's the only thing. And a singleton type, that's just another way to say the unit type. And so, well, you multiply something by the unit type and you get the same thing again. So we can construct this in a way where it lies directly over m.type. And so that's why this definition is okay. And our type checker, if we implemented this, would stop us if we didn't succeed in doing that. And then we can implement the, this should say m star.term. We can implement m star.term a by projecting out the syntactic part, and then we're good. And maybe just one thing to note, I'm using some kind of magical implicit notation that when I state something like this, well, underneath the modality, an element of m star.type is literally going to be an element of m.type. So that's, yeah, a nice little trick that we can do to make it easier to write this stuff down. That was the hardest thing. But the nice thing is that it's actually a bit easier than it is to do in the concrete setting. But what about the function type? So usually in the function type, okay, well, let's see here. We got to do two things. We got to say what the syntactic part of the function type is between two parametricity types. And then we got to say what the semantic part is. Well, the syntactic part, we already know what that has to be because we've already asserted that as far as the syntactic part is concerned, it needs to be m.rab. So that's that part. We can't, we've got no leeway there, okay? Now for the semantic part, well, it'll also turn out that we have no leeway there either, but maybe this is a nice place to point out the difference between the synthetic and the analytic parametricity structure. In the synthetic parametricity structure, when you define the function relation or the function structure, this is when you start doing all this crazy stuff like, okay, well, for all something from the left, something from the right, with the property that they're related, then if I apply the functions on both sides, then they're related in the other thing. And this can get arbitrarily complicated depending on how like jacked up your language is. And as PL theorists, we like to study maximally jacked up languages. So this can get pretty hard. And the nice thing is that here it's just the function type, because everything in sight is a parametricity structure. So the function arrow, it means the right thing. Someone, of course, has to do this interpretation, but it can be done at the beginning, ages past. So no one needs to worry about it again. So this is kind of fun. And then we can actually recover that complicated analytic definition as a consequence of the refraction of a parametricity structure into its syntactic and semantic parts. So that's maybe a nice little exercise that you can do. So this makes it, I think, a bit more fun and smooth as you develop these things. Let's see here. So for the Booleans, well, here we've got a bit more leeway, and I'll try to do the exact same interpretation as we gave before on the analytic side, but just to show how the synthetic one actually works. For this, well, what we're going to want to do is we're going to have a syntactic Boolean. And again, this is also, because it's under this syntactic thing, it's really a pair of a left Boolean and a right Boolean, but all of that plumbing just recedes into the distance in the synthetic setting. And then we're going to say when is it parametric, and we'll say it's parametric. So we're going to want to have a syntactic Boolean. We'll say it's parametric when it's either true or false. And what this ends up unfolding to is that both the left hand and the right hand side are true, or both the left hand side and the right hand side are false. So I put this red here because we actually have a type error. This thing is not going to be aligned. It's not going to have the syntactic part being bool. Why is that? It's actually going to have its syntactic part be the collection of syntactic Booleans that are syntactically equal to either true or false. We don't actually know that all Booleans have that property. That's one of the things that would be a consequence of the parametricity theorem. It's not part of our input. So consequently, this is not well defined. It's going to actually store too much data in the syntax. So this is where the semantic modality comes into play. So what we can say is, well, actually, what we're only going to do is just know semantically that it's either true or false. And putting it underneath the semantic modality wipes out any extra data that could have been fouling up the syntactic part. And now it lies over the right thing. So this is, I think, maybe our first actual use of the semantic modality. And it's very useful for this, basically. This is a phenomenon that is hard to see in the explicit parametricity structures or parametricity relations, because it would correspond to having like tau left be something that you can't even express in the language of system F. So this is something that arises in the synthetic setting that you have to take care of. Now to implement the constants. So we want to say what the parametricity structure of true is. So I guess I should have called this true instead of TT. I apologize for that. So this, it needs to be syntactically the same as TT with this. That's what we're contributing to the implementation of M star. So we're giving an element of this sem record here, and the first part has to be m.tt. That's non-negotiable, and then the second part has to be an element of this sem thing that such that you can show that it is m. This should be tt or true or whatever. I apologize for the inconsistency. So for this part, well, how do you introduce the sem modality? It's a monad. So we'll just use the unit, the return operation. And now our goal is a proof that either m.tt is equal to m.tt, again, sorry, or equal to m.ff. So we'll use in left, so the left injection into the coproduct, and then the proof is trivial. True is equal to true, and we're done. And that's how you show that the Booleans are parametric. So that was that's like proving a general parametricity theorem for a language. But what about proving a representation independence theorem for the queues that we started with? That's more fun and a little harder. So first of all, we got to get those queues into this language. So we know how to define the queue signature. It's just defined how we define it at the beginning. Okay. And what we're going to do is we're going to define an element, a syntactic element of that queue signature. And remember, a syntactic element, when you're making one of those, you're allowed to case split on whether you're on the left or on the right. And so we'll do that case split. And we're going to put the implementation of the ListQueue on the left side, and we're going to put the implementation of the BatchedQueue on the right side. And now, as far as the language paramtt is concerned, this is a single syntactic queue. But by the nature of what it means to be syntactic in paramtt, it's really two different queues, because you have basically two different copies of your language, one on the left and one on your right. And so this is a notation by which we can define this object. And then what we want to do is we want to define a parametricity queue. That is a queue that's not like syntactic. It's actually just unqualified. And we want its syntactic part to be queue left-right. Meaning that this is going to be, in essence, a proof that the ListQueue is related to the BatchedQueue. And this is where we're going to store the representation invariant. So just at a high level, what's cool is that we can use the same language to implement our original Q implementations. We can engineer them in this language, and then to prove that they are observationally equivalent, rather than unfolding into some kind of a model, we actually can just implement a third Q. And this third Q has this magical property that it somehow unites the two Qs. And this third Q is what I'm calling the letter Q here. So what is the implementation of the Q data type in for this third Q? Well, we're going to store an element of the syntactic queue. And of course, this unfolds to being an element of the left queue, of the list queue, together with an element of the batched queue. And then we're going to additionally store computability data that witnesses the fact that these two queues are synchronized, in the sense that if you take the batched queue and you flip it around and glue it together, you'll get the list queue that you stored. And so I am going to use the semantic modality to make sure that I don't end up saying more at the syntactic level than I want, because I want this to lie over QLR and not over some sub-object of QLR. And then I'm going to store in the fact that these queues are related, I'm going to store the invariant. I'm going to say, well, let me just store 3 lists that satisfy the invariant with the property that the queue that I started with is represented by those 3 lists, meaning that the first list is the list corresponding to the list queue, and then the second one is the list corresponding to the batch queue, the pair of lists corresponding to the batch queue. And then in order to implement the rest of the structure, for instance, to define the empty queue for this, well, I need to, first of all, have the syntactic part be the same as the original syntactic parts. So I'll just project that out from the syntactic queues. And then I need to store a proof that the empty list queue is related to the empty batch queue. And that proof here is just very simple. It's I have these 3 lists, and they trivially satisfy this property. So that's good. And then you can see how you might fill in the rest. You have to implement an insertion map. And what you're doing is you're defining a function between the syntactic queues, fine. But then you're also defining a function from parametric elements. So you're defining a function from these proofs that the queues are synchronized to a further proof that the queues are synchronized. So this shows that this is the way that the preservation of the relation arises in the synthetic setting. And then once you do this, you can again prove internally that any function from Q to bool will do the same thing on the left queue, which is the list queue, or on the right queue, which is the batch queue. And the way that you prove that is that you apply that function. You literally just apply that function to this implementation. And then you get something that has, so that started off with the extent being, the syntactic extent being the 2 queues. And now what function application does to an extent is that it becomes, the extent becomes the application of the function to the 2 queues. So C of list queue and C of batched queue. And then the cool thing is that because we define the booleans in a sufficiently discrete way, being 2 things being related in the booleans ends up meaning that they're equal. And so as a result, we get the representation independence theorem in the synthetic setting. So this is actually all a special case of something that we've been working very hard to develop for a number of reasons, basically over the past year. Although I have to say that it was in the context of this work that we first had the idea to do this synthetic stuff. But basically, synthetic Tate computability is my name for this idea of having a type theory extended by one of these bizarre magical propositions, which about which you don't really need to know anything. It's just an abstract proposition. And somehow this gives rise to all logical relations arguments. So this is basically the topic of my thesis. And maybe another way to think about this, which I have found very profitable lately, is that logical relations is a kind of phase distinction between syntactic and semantic. You've got stuff that is happening at the syntactic phase, and somehow this is independent of what's happening at the semantic phase. And this corresponds to the fact that even if your semantic part is empty, if you make a function out of that, you're still obligated to provide a syntactic part of the function. So there's a non-interference happening here. And this is essentially what is provided by this modal setup. And so Bob and I have written this paper, Logical Relations as Types, Proof-Relevant Parametricity for Program Modules. And this paper describes a much more complicated instance of the thing that I described today. But this is essentially where we first apply these ideas. And thankfully has been accepted modulo minor revisions to the journal of the ACM this week. So we're happy about that. And then the other application of this that we have is Carlo and I have finally proved normalization and decidability of judgmental equality for cubical, univalent cubical type theory. And so I would say that was maybe the most brutal battle test of this machinery, because it was something that basically nobody knew how to do. And we weren't really sure how to do it before either, but this made it actually somewhat easy to prove. So that was a nice surprise. And separately, Daniel has also used this to prove normalization for a general multimodal type theory, where you start off with like a mode theory that generates a bunch of complicated modalities. It's kind of above my head, to be honest, but it looked pretty good. And so he has used this method to prove normalization and reduce the word problem for that language to the word problem of the underlying mode theory. Basically, my little crusade, I think I've this is maybe one of the areas where Bob has influenced me the most, is that everywhere in sight I'm seeing different phase distinctions. So one of them is the classic phase distinction between static and dynamic in ML languages, and this idea that like static stuff does not depend on what happens at runtime. In fact, this was our original. We first understood the synthetic approach here in terms of static versus dynamic, and that's and then we later realized that syntactic-semantic was a further instance, and multiplying those two phase distinctions, orthogonal phase distinctions together was the point of our paper, Logical Relations as Types. And another interesting idea that Bob has suggested is the relationship between inlining and abstraction. So in a compiler, you want to inline stuff, but you also want to hide it from the programmer, because you don't want the programmer to depend on things. And so when your module system is so abstract that you can hide information, well, it's still not good to hide it from the compiler in many cases. And so this approach provides a way to expose things in a more fine-grained way, where the compiler can see underneath one of those little lock things, but the user can't. Resource usage is another one that Bob and you and I are exploring, where what the static, syntactic, the thing that's analogous to that is behavior. And the extra data that gets covers things is cost information. Another one that I think our perspective is sort of a special case of that of Paul-André Méliès and Noam Seilberger is the idea of refinement, where the lower level is the extracted code and the upper level is the like verification of logical properties. And finally, one thing that I've been looking into lately is information flow, a phase distinction between low and high security, and where the thing that corresponds to, in our case, a semantic modality, is used to hide information from lower security levels, hide information from clients that don't have permission to see it. So this is like, I think there's actually like a lot of possible applications here. So I'm curious if anyone has any other ideas, but that's kind of what we've been cranking on lately. Oh, and of course, the ultimate one where all this comes from is the idea of open and complementary closed subspace. And in fact, this idea of having that that weird proposition, the lock thing, it's ripped directly out of SGA4 from 1962. But there it was used in the context of topology and algebraic geometry, but here we're using it for computer science. So a lot of connections to be made. It's been a lot of fun. So I'll stop there, and I'd love to answer any questions that you may have.
Great, thanks. Yeah, that was very good. So does anyone have any questions? Bring up YouTube and see if there's any.
If I may, maybe I'll ask a question.
Oh, hey, how's it going? Long time no see.
Long time no see indeed. How are you doing, John?
Oh, pretty good, pretty good.
Excellent. I do have, so when people study representation independence, they often try to dodge this thorny issue of higher order store.
Yeah.
And I saw that in your manuscript, you very carefully explained that you don't want to think about this.
Yeah.
But still, do you have any thoughts on how this might help inform the study of representation independence for higher order store?
I think it's a really good question, and I'm not exactly sure what to do about it. My thoughts at this point are basically that store is, so while it is possible to treat higher order store in an equational way, I think that maybe this is not the right way to think about it. Like operationally, you know, for instance, many people like to think of even allocation as a non-deterministic operation, for instance. And once you add, you know, another way to think about store, by the way, is like you have like the interaction between a client and a heap. And a priori is not necessarily any reason why these interactions should be deterministic, although in some cases they are. And so my feeling is that with store, you shouldn't think about it as equations because it's not what non-determinism is. And instead, I would like to think of it as configurations that are subject to a transition relation. Although from my perspective, these should be configurations like equivalence classes of configurations under some structural congruence. And so how do you incorporate that into a setting like this? Well, I think that what you want is essentially some kind of a monad that is equipped with a transition relation in the logic. And then in the the synthetic Tate computability that you build over this, you should have some connectives that enable you to form things like weakest preconditions and so on. And I think that building in these weakest preconditions into the definition of, say, the parametricity structure of the effect modality is essentially what you would need to do. And if you can figure out a way to actually construct this stuff, which is by no means guaranteed, then one would have a way to talk about parametricity for these programs. But for me, it's very speculative.
Got it. Thanks.
Hey, anybody else have any questions before we head out? All right. Well, thanks again, John. I really appreciate it. And yeah, I thought this was really great. So
yeah, well, thank you. And thank you all for coming. It was nice to talk with all of you.
Yeah, and thanks everybody for coming, both in Zoom and on YouTube. So, and this will be recorded, so feel free to share it with others.
Cool. Great. Thanks, Harley. I'll see you all later.
Yeah, thank you. Bye, everyone.